I have to save the free body diagram. It seems like something that you could get like in one of those holistic health places. You know, you go in and they'll give you a free body diagram and chart your chakras. Okay, so yeah. I didn't say anything about that. Yes. So, yes. So, maybe you're not getting the story quite right. And if you do 75%, no. Or 80% correct. If you can't know 80% of the basic stuff, you don't deserve it. But wait. Wait. So, here's how the final will be structured. Part 1, easy problems. Really easy problems like that. Okay? Easy problems. But all the material, I mean not just, they won't all be this. Right? But problems along the lines of the level of the problems on the placement exam. So a lot of you maybe didn't take the placement exam because you got AP credit, but they're straightforward, easy problems. Of course, they cover everything, so, you know, like write the Taylor series for e to the 2x or something like that. But covering all the material, but easy, straightforward problems that if you know how to do the material in this class, you should be able to get through it in half an hour. And if you do 80% correctly on that, then you get a C for sure. Okay? So if you do that 80% correct, you get a C. And then the rest is to determine whether you get an A, or a B, or a C. Okay?
And if you don't get 80%, you fail?
We have to negotiate. I don't know.
What if you do really well? What if you get a bomb?
I'm hoping that won't happen to anyone. So, you should focus on the first part until it's done. Because the first part is supposed to be a measurement of the minimal skills in this class. And if you can demonstrate mastery, if you demonstrate the minimal level of understanding, then you should pass the class. And so that's what the first part is for. And then the second part is to decide whether you pass with a C or an A. Yeah. Could you guys hold it down a little bit so I can hear him? Yeah. No. The first part is going to be a minimum hurdle. If you can clear the minimum hurdle, then you're guaranteed to pass. Beyond that, we'll look at the rest. So, I mean, you can think the first part is worth, let's say, 50 points. And in order to get a C, you need a 50 on the test. Okay? So, other items. So there's that issue about the final being in 2 parts. There's a basic easy part that everyone who deserves to pass should be able to do relatively quickly. And then there's the rest, which will be the harder problems that will be like on the previous midterms. Right? On the previous midterms, there were a couple of easy problems scattered among harder problems. Not really? Well, there should have been a couple of easy problems scattered among the harder problems. Certainly that was true in the first midterm. On the second midterm, more of the problems were middling difficult. There was no crazy hard problem, but there was no trivial problems either. The other thing is, sorry, I don't remember whether it's Javits 111 or 110. One of them has I don't know, it holds 103 people. I think that's 111, right? I think so. So the room, the biggest room that I could get was that one. So they gave me Javits 111, Friday at 2:15, and I will just do whatever problem people want. Also, I have my office hours on Monday, but so if you have questions that you want to ask, specific questions, during the week, you can make an appointment. I'm around. You can make an appointment and come in. So I'm not holding scheduled hours other than my usual hours on Monday next week, nor is Professor Doniphan. But both of us, if you say, I need help, I really don't understand partial fractions, when can I see you? And then we'll say, okay, how's Tuesday at 2? Or, no, I'm giving the final answer, so I won't say that. How's Thursday at 2? Or whatever. Okay? Any other questions about where the final is, what it is, how it is, why it is? Okay, so let's move on to doing problems, reviewing. We left off in techniques of integration. Somebody asked me to do a partial fractions problem. So let me briefly review partial fractions. So you use partial fractions when you have an integral like, maybe I will do, well, okay. When you have an integral which has a bottom that you can factor, and then that splits it up into, so something like, let me just already leave it factored. So say I have an integral like this, and 1, you want a 1? Okay, I don't care. Say I have that integral. I could put something more complicated on the top, but make it more complicated. How about that? Okay? So what the idea here is that we want to split this up into two easy integrals that look like this, but we can't quite. I mean, so it's just algebra to try and split this up. So we just forget about the integrals and we just do algebra. So we say, if there are a's and b's so that this is true, what are they? Note that it's important. A couple of things that are important. We must have the degree of the top smaller than the degree of the bottom. If the degree of the top is larger, you have to do long division or some other way to reduce the degree on the top. You have to split out all of the stuff that is higher degree than the bottom. Let me hold the special case for a minute. So we just do this. So it's just an algebra problem. So we cross multiply, and we need to find a and b, so that 2x plus 1 equals a times x minus 1 plus b times 3x plus 2. And either you can now multiply this out and equate coefficients, we can do it that way, or you can choose judicious choices of x to kill off the factors. I like that way better in most cases, but sometimes the other one's easier, so let me do that way first. So because this has to be true for all values of x. So that means that if we choose special values of x, it still has to be true. So if x is 1, we have 2 times 1 plus 1 is 3. This is 0. And this is 5b. So that tells us right away that b is 3 over 5.
No.
What? No? What? So if x is 1, 2 times 1 plus 1 is 3. A times 1 minus 1 is 0. 3 times 1 plus 2 is 5 times b is 5b. So if x is 1, 5b is 3, so I know right away that b is 3/5. And if x is negative 2/3, then that tells me, well, these numbers are a little grosser, but okay, negative 2/3, so that's negative 4/3 plus 1 is negative 1/3. And this is negative 2/3 minus 1 is negative 5/3. And this is 0. So that means that A is 1/5. Okay? Do you want me to go through the other way?
Yeah.
Yo.
Yeah.
Yeah, no. Okay. So the other way, which is completely equivalent, but sometimes a little easier to use, I guess I'm going to give up on my free body diagram. Oh well. That one is just stuff. Okay, the other way, which is equivalent, is we multiply out this thing. 2x plus 1 equals ax minus a plus b, 3bx plus 2b. So that means that a plus 3b is 2 because I'm matching the coefficients of x, and 1 is minus a plus 2b. And then you solve these equations simultaneously. Here you would add them together, get 5b equals 3, and then substitute back and get a equals 1/5. Okay? So, should be the same. Okay, and then, does anyone need me to do this integral? I'll just do it, it's quick. So the integral, 2x plus 1, 3x plus 2, x minus 1 dx is equal to the integral a is 1/5 over 3x plus 2 plus the integral 3/5 over x minus 1. So this is 1/5 the log of 3x plus 2 because we make the substitution u equals 3x plus 2, except this is a 3x. So that means if u equals 3x, then du is 3 dx, so we have to divide by 3. So am I saying that too fast? So this is 1/15 log 3x plus 2. And then this one, du is dx. So this is just 3/5 log x minus 1 plus the constant. Did I do this too quickly? Everybody's okay with this, right? Okay, so again, well, right. So one caveat with partial fractions is sometimes you can't reduce the factors. You're left with a quadratic factor, or you have a repeated factor. So if I have something like, let me just put a 1 here, over x cubed, x squared plus 1. Suppose I want to use partial fractions for this, then I would split this up. Maybe I want, let's put a x minus 1 here too. I'm not going to actually do it, I'm just going to set it up. I would split this up into 3 things. And what I need is that the degree of the polynomial on top with the a's, b's, c's, and q's in it is 1 less than the one on the bottom. So here I would have ax squared plus bx plus c. So I would have to find three variables in order to understand what's on top of the x squared. Here I would have, I'm not going to use d, e, x plus f, and here I would have a g. So So I'm not going to do this one because it's quite complicated, but I just want to point out that you split it up into each of the factors, and the degree of the thing that goes on top is one less than the denominator. Okay? So this one would certainly not be on the first part, and if it's on the second part, I would expect most people to blow it. All right, so let me leave that. What else do we have to cover here? I think that's it for the techniques of integration, right? Because I did most of them last time. Any other techniques of integration I need to review? No. Okay. So, what else was I? So the next topic is volumes. So now we're into chapter 6, I guess. Oh, no. I missed improper integrals. Sorry. So improper integrals would be something like the integral from 1 to infinity of 1 over, doesn't matter, x squared dx. So this is saying if we have this curve 1 over x squared, and we look at this area, is it a finite number or is it not? And the only thing with improper integrals is that, well, this doesn't really make explicit sense unless we extend the definition of integration, because we can't put infinitely many little rectangles under here. So we just remember, we just extend this to mean this is the limit as m goes to infinity of the integral from 1 to m of 1 over x squared dx. So we just do this integral, which is very easy, and then we take a limit. So the integral of 1 over x squared is 1 over x negative. And we evaluate it from 1 to m. So this is the limit as m goes to infinity of, lost my train of thought here, negative 1 plus negative 1 over m. Yeah, wait. So, no. The derivative of negative. What am I doing? Sorry. Isn't this right? Yeah. The derivative of x to the minus 1 is minus x to the minus 2. So the derivative of this is this. So, yeah. So this is right. And so, but something's wrong here. Oh, I did this backwards. Sorry. It's minus 1 over m plus 1. That's better. Okay, and then if we take the limit, this term goes to 0, so I get 1. So this guy converges to 1. So we would say that this converges to 1. Okay, so this is pretty straightforward. And I know when you first saw it, it seemed very confusing because we had this infinity in there and all sorts of things. But this is very similar to the kind of stuff we're doing that we did with infinite series. So maybe after having to deal with the infinite series, this makes a little more sense, or at least you've had a little more practice. Of course, it will diverge if I change the power around. I could get one that diverges or converges or whatever. But the idea is very simple. The other situation would be if the thing blows up somewhere inside. So, for example, the integral from 0 to, I don't know, 0 to 4 over 1 over x minus 2, over dx over x minus 2. So this one would diverge. All right, this blows up at 2. We have to check. So this we have to write as the integral from 0 to 2 plus the integral from 2 to 4. And then take the limit. This is a limit as x goes to 2 from below, and this is a limit as x goes to 2 from above, but this blows up, right? So this is the log of x minus 2 evaluated from 0 to 2, log x minus 2 evaluated from 2 to 4. But now I have to take the limit here, and here. Yeah?
If one of them is average, you don't have to.
If one of them blows up, you don't need to bother with the other. Right. So this 2 from below of log x minus 2. So this diverges. Of course, I could change the problem and make something that converges, but if you put a square root there, it's going to converge. But we're okay. All right? So these are the two variations on improper integrals. I feel like I'm forgetting something else. You just look here. No, that's it. Oh, no, it's not it, because we also have Simpson's rule and stuff like that. So we also have, so any questions on improper integrals? Okay, so the other topic in chapter 5 that I just forgot about, and now just remembered, is, okay, Simpson's rule. So the idea here is to just think carefully, or not even that carefully, think a little bit about what the integral means. So if I have some integral like that I can't do because there's no nice formula for the integral of sine x over x. Although we can do it by power series, there's no closed form for this. What we do, I want to integrate from 1 to 2, and my function, I don't know, looks something like that. It doesn't really matter too much for what we're doing. What I do is I chop this up into some number of pieces, and I just put little rectangles or little shapes underneath it to try and calculate the area here. So we have sort of 3 methods that we tend to favor. So the most efficient one, well, so the easy to remember would be, say, should I do 4 or doesn't matter. Easy to remember would be, say, the trapezoid rule. So we choose some number n, and this is how many, plus or minus 1, how many points we're going to evaluate our integral at. And so maybe I will give you n, probably I will give you n. We choose n, and for the trapezoid rule, we calculate the area of that figure. So the trapezoid is, the area of a trapezoid is the base times the height, the average of the 2 heights, the right height and the left height. Right? So here, I've chosen n. In this case, I'm taking n equals 4. So I divide this up into 4 pieces. So that means that this point is at 1. This one is at 1 1/4. This one is at, let's call that 5/4. This one is at 6/4. This one is at 7/4. And this one is at 8/4, which is also known as 2. I know that 6/4 is also known as 3/2. And so to use the trapezoid rule, what we would do is find the area of this. So we're going to take the width of the base. So here the width of the base is 1/4 every time. And so we're going to take the width of the base times, and now we just add up the heights at each of these points, but we remember that the ones in the middle get double counted because we're going to average them. So I want to average f of 1, which is the sine of 1 divided by 1, plus, and now here, at 5/4, from this one I'm going to count it once, and from this one I'm going to count it once. So this will be twice the sine of 5/4 divided by 5/4, twice the sine of 6/4 divided by 6/4, twice the sine of 7/4 divided by 7/4, and then here I've only got one side, so I only count it once. And I'm averaging these numbers, so I have to divide by 2. So this is the trapezoid approximation for this integral. Another way we could do the same thing, I'm not going to get through this, am I? Another way we could do the same thing is take the midpoints and just add them up. Do I need to review that? No? Nobody wants to hear it? Okay. So another one we could do is the midpoint rule, which is the same idea. We just add up the heights of the rectangles that go through the midpoints. So that would be this picture. Take this, plus this, plus this, plus this. So I have to evaluate these points. So I only have 4 numbers. And then I also have Simpson's rule, which is more complicated because I'm actually fitting a parabola here. So let me just draw the picture again. So if I'm doing Simpson's rule, I'm actually, with n equals 4, means that I'm taking 2 rectangles and I'm putting little parabolas that fit best. And the pattern on each one of these is I take one of these and one of these and 3 of those. But since this one gets double counted, it actually goes 1, 3, 2, 3, 1. So it would be these same numbers, actually. So but here I take 3 of these guys, 2 of those guys, 3 of those guys, and just 1 of those guys. So it's 1, 3, 2, 3, 1. 4. Oh yeah, it's 4, isn't it? Sorry. You're right, it's 4. Yes, because, yeah. 1, 4, 2, 4, 1. And since I'm averaging them 3 at a time, but I'm also averaging, I divide by 6. Oh, wait a minute. 3. 3. No, because the n is n over 2. Yes. And a half here. No, a quarter, because they're a quarter apart. Yes. Okay. 6 is for the other one. And there are error formulas here that tell you how many things you need to know. If I ask a question on the error formula, like I say, how many terms of sine x over x would we need to get the error, to get the integral within 3 places, or 10 to the minus 15, or whatever it is? There's a formula, and you just solve it. The thing that's tricky is you have to remember that the formula depends on, in this case, the maximum of the second derivative over the interval, or in this case, the maximum of the fourth derivative over the interval? Yeah.
That would be on the second part, right?
Yeah, that would not be a first part kind of question. Okay, so that's, everybody okay with these? At least enough for today? Okay, so now we should move on to volumes, I guess. So, the basic idea of all of the volumes, whether they're volumes of revolution or volumes with a given cross-section or whatever, is that the volume of a solid is the integral of the area of a cross-section d whatever, dx or dy. So if I have some wiggly object here with an easily understood cross-section, then I can find its volume just by slicing it and integrating the volumes of the slice. Okay? So, if I have, so maybe I should do an example of this, but so here the area, the volume, well, okay, so maybe I should do a specific example. So, and all of the problems that we do, even the ones where you can work out a formula like the volumes of revolution with the washers or the discs or whatever it is, it's really just this. Everything is really just this. Think about how to slice it up. The slices have a nice description, and then you just add up the area of the slices. So, for example, so suppose we have had one in mind. Okay, so suppose we have some shape. Let's say it has so I have something that has a square cross section. I don't know if you can see. Let's cut the end off. So suppose I have a shape that looks like that. So the base looks like, so this is, I'm drawing it a little bit weird. This is the x-axis, this is the y-axis, but I laid it down and put the thing, usually we make x come out of the board. Let's make this be the x-axis. This is the y-axis. And so the shape of this thing, the base looks like this. Okay? And let's say, just for argument's sake, this is the line y equals 3 minus x. And it goes from, well, here is 3, and here, let's put it at 2, at 1, 2. And the cross section the cross section is perpendicular to the y-axis are squares. Does everyone know how to do this? Some people yes, some people no. Okay, so what this problem is saying, these slices, if I slice it this way, I see squares. I can also slice it the other way, but it's a much more complicated thing to do. So let me do it this way. So this means that to do this, I would want to set this up. So somebody tell me how I would set this up. You know how, you nodded. So, okay, what would I integrate? What are the bounds on the integral? 0 to 2. And I'm integrating dx or dy? Dy, because they're, right? So 0 to 2 dy tells me that I'm looking at slices that go like that. From starting off from y equals 0 to y equals 2. Right? So rewrite this as x equals, okay. So rewrite this as x, let's put it here, x equals 3 minus y. That was easy. And so now what do I integrate? That's where, yeah. Because I have sitting over here a square. So if I look at height y here, some arbitrary height, I have a square that is 3 minus y wide by 3 minus y high, and it's dy thick. I'm just adding up all those little slices of cheese. So I have 3 minus y squared equals. And that's the moment. Okay? And do you want me to do that? I mean, square it out. We'll make the substitution u equals 3 minus y. And so du is negative dy and the top of it. Okay? Everybody okay with this? We can, of course, make it more complicated where the cross-section is a disk. Or, so, I mean, here, obviously, in this one, I can't have the cross-section being a disk. But I could have a similar setup where I take something like, let's just take the same object and do things to it in various ways. Oh, I'm sorry. I forgot to mention one other thing in terms of, so this is a pause. I am putting up, it's not quite finished, but it will be finished probably tomorrow. No, it's extra credit. So you don't have to do it. But you can do it if you want. Okay. So, I'm adding another WebAssign, which is optional, which has somewhere on the order of 60 to 70 problems. Do as many or as few as you wish. Each one counts for half a point. This adds on to your homework problem, but if you have more than 100% on your homework average, I don't care. Now I'm ready for battle. Okay, so I don't know where it is, so I have to leave it. So there will be a WebAssign going up over the weekend, which is optional. Do as many or as few as you wish. Huh? Monday, the final. So due by the final. But it's not due. It's just once you do as much as you want. So then do it. All right. That's to study. So what is this WebAssign? All I did is I took problems from the beginning to the end. Some are straightforward, like part 1. Some are harder, like part 2. And I put a bunch of problems. So, there's a problem like this on there. There's a problem like... Okay, so let me come back to this problem. This, which side's left? This side? This side? There? Okay. Now I really look ready for battle. I can give myself like a thing like, I forgot his name, the guy who did the ear off. Mike Tyson. I could get like a Mike Tyson bingo. Okay. Because I look so much like Mike Tyson. Yeah, I do. Okay. So, let's just continue this a little bit. Suppose I took this shape and I revolved it around the axis to get a piece of a cone. Then the process would be similar. Right here, this is still the line x equals 3 minus y. I revolved it around the axis. It goes from 0 to 2. The cross section is no longer a square, now it's a circle. So this would be the integral from 0 to 2 of pi r squared dy. If I revolved it, instead of around the line y equals 2, some other line, well, we'll get some other thing. If I revolved it around the x-axis, so I revolved it this way so that I would get something that looks like a cylinder with a point on it, then it's more complicated. I could either do this by slicing it this way, in which case I have circles for part of it, and I have two functions that I have to integrate. So I could integrate this dx as the integral from, well, if I'm doing it this way, this is 1, this is 3. So I could say, I could integrate from 0 to 1 of 3? No, the height is 2, right? Of 2 of 4 pi. That's one of these circles in this bit. And then I have to integrate from 1 to 3 of this line, which is 3 minus x dx. Or I could slice it the other way and have washers. Anyone want me to do the washers? Yeah? Okay. So does everybody understand where this came from? Yes?
Where did you get it full time?
Okay, so I have this thing that looks like a very short pencil. It has a cylindrical bit, like that, and then on the end it has something that comes to a point. Oops, I guess the boom is right? Okay, so, I mean, I've exaggerated this width. That's 3. So, this part, the height is just a circle of constant radius. What is the radius? The radius is 2. So what is the cross-sectional area of a circle with radius? What is the area of a circle with radius 2? Pi r squared. R is 2. So that's 4 pi. So to prefer, I could write that as 2 squared times pi. So for this part, the radius is constant. So I have to integrate one function to get this part. It's of length 1, so it's really just 4 pi. And then this part is a little more complicated. It looks like that. Okay? Okay. So I could also, if I were, I don't know why I would do it this way, but I could do it this way. I could think, I take this shape, and I take these slices, dy, and I revolve them around the axis. So what I'm doing is I'm decomposing this thing into a bunch of concentric shells like this. Right? So I have a bunch of little tubes, and I want to find the surface area of each of these tubes times its thickness. So this would be doing it by shells. Sometimes you have a choice of whether you want to do it this way, and sometimes it's really the easiest way is to do it this way. So if I wanted to do this for some reason, so some people and some problems say do this problem by shells. I won't say that. If you want to do it by shells, do it. If you want to do it by washers, do it. So do it by whatever method works. If I wanted to do this by shells, then that means that what I have to integrate is the area, the area of one of these little cylinders. So these cylinders go from, if I take a typical one, it looks like this. The radius here is y. The width here is, it goes from 0 to 3 minus x. And if I cut it open, so this distance, this is really, if I were to cut it open, it's a rectangle, which is 3 minus xy and 2 pi y around. Because the circumference of a circle is pi d, or 2 pi r. So that means that's what I want to integrate, is this area, 2 pi y, oops, 3 minus y. Yeah, 3 minus y. So I want to integrate 2 pi y times 3 minus y dy as y goes from 0 to 2. So those two integrals, if you do them, should be the same. I recommend that you not memorize the formula for volumes by discs or volumes by washers, but understand them and rederive them on an as-needed basis. Because you will not remember these formulas in 6 months. But if you remember the idea that you slice it and you find the area of a slice, that's something that should stick with you. Anybody want me to do more volume problems? Okay, yeah, yes? You have one in mind? I mean, they're all just like this. So they all come down to, so I only have 2 minutes, so I don't have time to do another volume problem. So if you have more volume problems you want done, let me know. Post it on Piazza or whatever. So let me move to one last topic that we can do in 2 minutes before I can take my war paint off, which would be something like, I don't know, average value or arc length. So you want it on the test. It has to be on the test. How can I not put average value on the test? Yeah, that's your birthday present. Okay. So we have some function like this. I was going to do average value, but I can do arc length. I'll write them both down. So for average value, all that means is I want to find some line where the area, well, if I slop off the top and stick it on the bottom, the area of this rectangle is the same as the area under the curve, so this is very straightforward. If I'm going from A to B, well, the area is just the integral from A to B of f of x dx, and so the average value is just divide that by b minus a. So this is why she loves it so much, because it is so easy. So you just calculate the area and you divide. Oh, I forgot to do area between curves. Oh well. For the arc length, for all of these things, it's sort of similar. The arc length is, we want to figure out by adding up lengths of a bunch of little segments. Well, these little segments, if you look on a small scale, are hypotenuses of triangles where their dx wide and their dy high. And so, by the Pythagorean theorem, this is the square root of dx squared plus dy squared. But we could rewrite this as 1 plus f prime of x squared dx. And so that means, so I don't have time to do an example, but I have time to write down the formula. That means that the formula for arc length is we integrate that. Yeah, I'm going to write it down again. So I integrate from the beginning to the end the square root of 1 plus the derivative squared dx. Because all I'm doing, again, is I'm finding the lengths, I'm adding up the lengths of these little hypotenuses. So there's really not time to do an example, so let's stop there. And I'll see you on Monday. And if you do 80% correctly on that, then you get a C for sure. Okay? So if you do that 80% correct, you get a C. And then the rest is to determine whether you get an A, or a B, or a C. Okay?
And if you don't get 80%, you fail.
We have to negotiate. I don't know.
What if you do really well? Or you get a bomb?
I'm hoping that won't happen to anyone. So, you should focus on the first part until it's done. Because the first part is supposed to be a measurement of the minimal skills in this class. If you can demonstrate mastery, if you demonstrate the minimal level of understanding, then you should pass the class. So that's what the first part is for. And then the second part is to decide whether you pass with a C or an A. Yeah. Could you guys hold it down a little bit so I can hear him? Yeah. No. No. The first part is going to be a minimum hurdle. If you can clear the minimum hurdle, then you're guaranteed to pass. Beyond that, we'll look at the rest. So, make it more complicated? How about that? Okay? So, what the idea here is that we want to split this up into two easy integrals that look like this. But we can't quite. I mean, so it's just algebra to try and split this up. So we just forget about the integrals and we just do algebra. So we say, if there are A's and B's so that this is true, what are they? Note that it's important. A couple of things that are important. We must have the degree of the top smaller than the degree of the bottom. If the degree of the top is larger, you have to do long division or some other way to reduce the degree on the top. You have to split out all of the stuff that is higher degree than the bottom. Let me hold the special case for a minute. So we just do this. So it's just an algebra problem. So we cross multiply, and we need to find A and B, so that 2x plus 1 equals A times x minus 1 plus B times 3x plus 2. And either you can now multiply this out and equate coefficients We can do it that way. Or you can choose judicious choices of x to kill off the factors. I like that way better in most cases, but sometimes the other one's easier. So let me do that way first. So if, because this has to be true for all the questions during the week, you can make an appointment. I'm around. You can make an appointment and come in. So I'm not holding scheduled hours other than my usual hours on Monday next week, nor is Professor Bonifant. But both of us, if you say, I need help, I really don't understand partial fractions, when can I see you? And then we'll say, okay, how's Tuesday at 2? Or, no, I'm giving the final name, so I won't say that. How's Thursday at 2? Or whatever. Okay? Any other questions about where the final is, what it is, how it is, why it is? Okay, so let's move on to doing problems, reviewing. We left off in techniques of integration. Somebody asked me to do a partial fractions problem. So let me briefly review partial fractions. So you use partial fractions when you have an integral like, maybe I will do, well, okay. When you have an integral which has a bottom that you can factor, and then that splits it up into, so something like, let me just already leave it factored. So say I have an integral like this, and 1, you want a 1? Okay, I don't care. Say I have that integral. I could put something more complicated on the top, but I mean, you can think the first part is worth, let's say, 50 points. And in order to get a C, you need a 50 on the test. Okay? So, other items, so there's that issue about the final being in 2 parts. There's a basic easy part that everyone who deserves to pass should be able to do relatively quickly. And then there's the rest, which will be the harder problems that will be like on the previous midterms. Right? On the previous midterms, there were a couple of easy problems scattered among harder problems. Not really? Well, there should have been a couple of easy problems scattered among the harder problems. Certainly that was true in the first midterm. On the second midterm, more of the problems were middling difficult. There was no crazy hard problem, but there was no trivial problems either. The other thing is, sorry, I don't remember whether it's Javits 111 or 110. One of them has a, I don't know, it holds 103 people. I think that's 111, right? I think so. So the room, the biggest room that I could get was that one. So they gave me Javits 111, Friday at 2:15, and I will just do whatever problem people want. Also, I have my office hours on Monday, but so if you have questions that you want to ask specifically, I have to save the free body diagram. It seems like something that you should get like in one of those holistic health places. You know, you go in and they'll give you a free body diagram and chart your chakras. Okay, so yeah. I didn't say anything about that. Yes. So, yes. So, maybe you're not getting the story quite right. And if you do 75%, no. Or 80% correct. If you can't know 80% of the basic stuff, you don't deserve to pass. But wait. Wait. So, here's how the final will be structured. Part 1, easy problems. Really easy problems like that. Okay? Easy problems. But all the material, I mean not just, they won't all be this. Right? But problems along the lines of the level of the problems on the placement exam. So a lot of you maybe didn't take the placement exam because you had AP credit, but they're straightforward, easy problems. Of course, they cover everything, so, you know, like write the Taylor series for e to the 2x or something like that. But covering all the material, but easy, straightforward problems that if you know how to do the material in this class, you should be able to get through it in half an hour.